All right.
Okay.
So let's start.
Okay. Good afternoon to everyone that's here in the session, Inverse Problems and Applications. We will begin with our first talk. That's the title is Fast and Accurate Reconstruction of Three-Dimensional Axis-Symmetric Scatterer. Carlos Borges will give the talk. He's from the University of Central Florida. Okay?
All right, thank you very much for the invitation to the organizers. Yeah, you already said the title there. This is a joint work that I did with my office mate when I was in NYU in July. Now he's in Zhejiang University in China. Okay, so all right, so in general terms here, we're interested in solving inverse scattering problems.
Sorry, Carlos, but you haven't
Sure.
shared your screen.
Oh, I'm really sorry. I thought that I did. My bad.
I thought you were talking before the screen.
No, I'm sorry.
No, that's right.
So, do you guys can see the screen now?
Yes.
Okay,
yes.
I'm sorry about that. I thought that I was already sharing. My bad. So, as I said, it's a joint work with June Lines there, and I think I was here. So, we're in this talk, I'm interested in inverse scattering problems. So, problems that, you know, pretty much you have some sort of measurements of a scatter field. So you send a field to a domain or a system, and this field is scattered. And from this scatter field, we try to obtain some properties of this domain. So you have several applications of those problems, such as in medical imaging, when you try to find, you know, where like to make imagings inside of people and where to find tumors and other stuff. Or you have applications here when you want to do oil and gas prospecting, where you have in most times like some sort of pistol here that shots the acoustic waves to the bottom of the ocean. And you have this like small line of sensors here measuring the scatter field. So you want to find where's the oil. And finally, like you have, of course, several defense applications in radar, sonar, or like even like finding mine objects and other stuff. So I'm gonna focus here in particular in recovering three-dimensional objects that are axis-symmetric. The main application for this case here is, you know, if you want to find where are some you know, mines in land mines in the field, or even sea mines, because you like for demining operations, it is very important. And mines in general, they have a very pretty close to axis-symmetric shape that you're trying to recover there. Okay, so there are some challenges in those problems, and one of the challenges is the computational aspect that it gets very it's very difficult to simulate problems in 3D. They are expensive, both the forward and inverse problem. The other aspect is that when you are solving an inverse scattering problem, and what I'm doing here is that I'm gonna consider this problem, I'm gonna recast as an optimization problem. You're gonna need some sort of iterative method, and those iterative methods, they get very expensive because you have to solve several forward problems in 3D. And a third challenge that is very important is the challenge regarding the resolution that you want to reconstruct those methods, because we are very limited here to the frequency of the wave that is impinging the obstacle. If your wave has a very small frequency, you cannot get a lot of detail. If it has high frequency, then you can have some detail. But like high frequency also has its setbacks, because high frequencies require a lot of, it's very computationally expensive to solve a high frequency problem. And also we're gonna see later that due to the way that the functional behaves, you might not get your initial guess for the reconstruction has to be very close to the object that you need to reconstruct. Okay, so just to cite here some literature review, like there are some working forward or solver by those authors here. For inverse scattering in single frequency in 3D, you have those authors. And for multi-frequency, this last one here, this last line, we are gonna be dealing with the type of work that started with Chen and Gangbao have been doing for several years. Okay, so let's go here for the forward scattering problem. So pretty much what is the idea in the forward scattering problem? You have some sort of obstacle. In this case, we're considering a sound-soft impenetrable obstacle. We send a wave in this obstacle, and in the forward problem, we want to know what is going to be the scatter field of this wave, or of this obstacle. So to obtain this scatter field, we have to solve the problem here that is showing on the right of this slide, where you have that the total field is going to be equal to the scatter field and the incident field. This total field is going to, it's going to solve the Helmholtz equation in the domain outside of the obstacle. And since we are considering sound-soft impenetrable obstacles, the condition in the boundary is that U is going to be equal to 0. And moreover, like I apologize, moreover, we have here that the field, the scatter field should suffice the Sommerfeld radiation condition here in the last line. Okay. So to solve this problem, instead of tackling the partial differential equation directly and applying some sort of finite element method with absorbing boundary conditions in an artificial boundary, we are actually going to solve using an integral equation approach. We're going to apply some potential theory. So we're going to consider the two potential layer operators, the single and the double layer operator as they are, with the Green's function being the Green's function for the Helmholtz equation in 3D. And we're going to apply those guys in the bound, like we are going to write the scatter field as a combination, a linear combination of those two layer potentials, and we're going to apply in the boundary of the equation. And using some jump conditions that happen there in the boundary for the operators, solving that PDE becomes equivalent to solve this integral equation in the boundary here, where you have the density of the operator divided by 2 plus G plus I, that is a K missing here, and I apologize, IKS phi is equal to minus the incident field, okay? So pretty much the forward problem is going to be the solution of this operator here. So since our obstacle, now we're going to apply this, the symmetry of the obstacle. So we are considering that the obstacles here are axis-symmetric. So we are going to take that the boundary of the obstacle is going to be represented by a one-dimensional curve that is going to be rotated around the z-axis. So the nice thing of doing that is that we can actually turn the solution of that integral equation into the solution of several different smaller problems instead of a general 3D problem. So the idea is that we're going to apply some separation of variables in the azimuthal angle, and we're gonna Fourier decompose the resulting problem. So pretty much what happens is that we write the fields as these linear combinations of those plane waves, and we will obtain a sequence a sequence of decoupled linear integral equations here. So instead of having that big equation in 3D, we have those equations here in the line. And each one of those operators are going to be given by these new single layer and double layer operators that where GM is going to be the model Green's function. It's very similar to the other function, a little bit easier. So the advantage of applying this is that instead of, that big equation, now we're going to have a sequence of equations for each one of the modes of the decomposition that we choose. And all those equations, they are uncoupled from each other. So much easier to solve than the previous one. So the quadratures to be applied are much easier, and the systems are going to be much smaller to solve. For example, if the obstacle is O of 1, each system is small enough that we can solve applying a Gaussian elimination of with O of k to the cube. And since the number of modes that you're going to need to resolve your field is going to be approximately O of k, the total expense of solving this problem for a single instant wave is going to be O of k to the 4. And if you have nd instant waves, it just becomes O of k to the 4 plus the number of instant waves times k squared. Okay. So this is pretty much the explanation what we've done to build our forward problem solver, which needs to be very fast. So now for the inverse scattering problem, we are changing a little bit. So before we had the domain, we have an instant wave, and we found the scatter wave in some sensors. So now in the inverse problem, what we know is that we have an instant wave. We have the scatter field measure in some sensors around, around the obstacle, and we want to recover the shape of the obstacle here that generated that. So pretty much we have the measurements of the fields, whatever the sensors are. You have a forward model that it takes object and brings to scatter fields. And what we want to do is that we are going to recast this problem into a optimization problem where we want to find the shape here of the obstacle that minimizes this objective function here. What is interesting in this problem is that this problem is, like most inverse problems, non-linear. You pose it, and that is the part of being computationally expensive because we are dealing with a Helmholtz equation with several incoming waves and with an iterative method. Okay, so to get this this recovery of the obstacle, we created actually a two-part framework that is going to use this property of the obstacle of being axis-symmetric. So the idea first is to find, in the first part, the axis of symmetry of the obstacle, and in the second part is to do the nonlinear optimization problem as before, and to recover a shape, a generating curve that parameterizes the boundary of the obstacle, the curve that, when rotated, parameterizes the boundary of the obstacle. So to find the axis of symmetry, we have a three-step procedure that pretty much we evaluate the far fields, we get the measurements of the field, we turn those measurements into far fields. Then once we turn the measurements into far field, we use the far fields and some properties regarding invariance over translation to find the direction. And later, after we found the direction, we find the location of the center of the obstacle. So to find the axis of symmetry, we're gonna use the far field pattern. There's two theorems here. One says that the far field pattern is symmetric with respect to the axis of symmetry. And the second one is that if you shift the domain omega, simple changes in the phase of the far field, it's not going to change the modulus of the far field. So let's just go through really quickly here into the step-by-step of the procedure, of this procedure. So first, what happened is that once you have the scatter field, we are going to calculate how would be the density to generate the scatter field in a certain ball that would contain the obstacle. Once we are done that, we calculate the far field given this density in the obstacle using those two integral equations. To determine the orientation, what we're going to pretty much is using this far field, and we're going to check if the modulus of these far fields are going to be horizontal across the section, taking different angles between 0 to 2 pi and 0 to pi. Once we get, this is pretty manual. Once you move around this module of the far fields through those this grid of angles, and you find one that is very close to the axis, it's very close to be symmetric, it means that we are in the axis of symmetry. Finally, to determine location, we're gonna have to use two waves. One wave going into the x direction and the one in the y direction, and then we're gonna measure those two fields there. So what the theorem 2 says is that, like, we can find C1 if we use the real imaginary parts of this field here, they are symmetric with respect to those angles. And we can find C2 if we do the same thing here with respect to those two other angles with the field generated by the other field, the other incident wave. Okay, so once we have the axis of symmetry, we go to recovering the shape of the generating curve. And what we're going to do is that we are going to apply a damped Gauss-Newton method in using single frequency data, and we are going to represent the domain by a trigonometric polynomial, like pretty much like some people did before with star-shaped objects. So the way that we are going to regularize is that the number of modes represent this trigonometric polynomial, the number of terms is going to be proportional to the wave number. Okay, so the only thing here that needs to be addressed is that, like, okay, so you deal with the nonlinearity and the nilpoteness. The only thing is that, as I said before, there is a limitation on the detail that you can recover of the obstacle. It's going to be proportional to the wave number. So to obtain as much more detail as we can, the more detail that we can, what we're going to do is that we're going to use multi-frequency data. And when we are using multi-frequency data, we're going to apply this algorithm here called the recursive linearization algorithm, which is pretty much an algorithm that does a continuation in frequency, solving that problem. So we are going to solve the problem as a sequence of single frequency problems, going from lowest frequency to highest frequency, being that the solution of the previous frequency I is going to be the initial guess of the problem at I+1. Okay, so the problem solved by single frequency has to be this one here. What we pretty much do is that we are going to choose an initial guess, gamma 0, and then we're going to update this initial guess in this way here with the Gauss-Newton method, where you find the update of the curve to be calculated solving this problem here, where we call this operator here on the left side the Fréchet derivative of the forward operator, and it's given by solve this Helmholtz equation here. The nice thing of solving this problem is that you can notice here is the same, it's the same PDE that we solved for the forward problem. So all the machinery that was built to solve the forward problem can be reused to solve this type of the inverse problem. All right. To treat the oppositeness here, we go back to what I said, that you have several different ways to solve that. You're gonna have to do some regularization, but you can do truncated SVD, Tikhonov, or some sort of band limited representation of the domain. We are going to with the last option, where we represent the domain in a star-shaped sense, like this that I put here. The gamma is equal to a trigonometric polynomial times cosine of angle, sine of angle. And this trigonometric polynomial is going to be limited by the number of nodes. So that is what I mean by the band limit representation of the domain. And this number of terms of the trigonometric polynomial is going to be proportional to the wave number. So one thing that you do when you are solving this single frequency problem is that you notice that at low frequencies, your wave number is low, so your wavelength is very large. The resolution that you can recover is very small. So if you use like a very simple, you will start from a simple shape, and you apply the single frequency, single frequency inverse scattering problem at low frequency, you're gonna have a very blurry reconstruction of the obstacle, okay? On the other hand, if you have a very high frequency and you try to solve the problem, you see that the convergence of the problem is going to depend on your initial guess, which is gonna need to be very close to your obstacle. And at high frequency, you have a lot of detail on your reconstruction. So you have this trade-off that at low frequency, with a simple initial guess, you get a blurry solution. Of higher frequency, with a very close to obstacle initial guess, you have a very good reconstruction. So using this idea, Shane proposed the recursive linearization algorithm that is nothing more than you're applying a homotopy there to solve this problem, doing a continuation method in frequency for that functional that we have for the forward problem. And the idea is that you will start at a very low frequency, and with the lowest frequency that you have, with a simple initial guess, get a solution, use this solution as the initial guess of the next frequency that you have. So what happened is that if the step between one frequency to the other, from K0 to K1 is really small, so you are fine. The chance that you are going to be in the local set of convexity of all the functionals is going to be high, and then your method is going to converge. Okay, so this is the general idea of the method. Let me present some examples here. So the first example is just to find the axis of an ellipsoid, because it's the most manual part of the obstacle. So we try to find the axis for this ellipsoid here, given the scatter field. And what we do is that we find the first part of the procedure, and we have here the field before applying the rotation and the field after applying the rotation. So after we apply this rotation, we are able to find the angle of the obstacle here, as you can see, the pi over 3 and pi over 4. Once we have that, we can use that to look at the field of the obstacle and before the rotation, after rotation, and see where is the exact symmetry of the field. Okay. And from that, we can find also the center of the obstacle according to those guys. So let's go now for the part of looking at the local sets of convexity of the field. So just to show what happened with this functional here, the f of like the residual that we are trying to minimize. So we try to recover. We printed the functional here when we have a circle, a sphere of radius 1 with center at 0, and we try to recover a polynomial, only the radius of this sphere. And actually, what we're plotting here is the value of the functional for different values of k, and also the local set of the size of the local set of convexity on each one of those. So as you see here, for k equal 1, this local set of convexity is huge, but as you increase the k, the local set of convexity starts to get smaller with the frequency. And you can see here by this side. So this justifies the use of the recursive linearization algorithm. This is just a table with those values. I think I still have 1 minute. I'm going to try to rush here just to show reconstruction of the shape. But like pretty much what we do here in the next example is that we try to reconstruct this shape here on the left using these different configurations here. In one configuration, we send the incoming wave in this direction, and we have these sensors. In the other, we have here we have full aperture. Here we have like limited aperture. And bottom line is that if we have full aperture, we are able to recover the object. If we have limited aperture, we are able to recover some sort of funky reconstruction of the obstacle. It's not very good. It doesn't have a lot of detail. And finally, just to finalize here, I try to recover this shape here of a mine, which has some corners, and it's very interesting in terms because it's a general application. Here it has the proportions of a small mine, and we use multi-frequency data. And what happened here is that when we are trying to reconstruct, we went up to a higher frequency. And we noticed that when we are reconstructing, we started to see this very wiggly reconstruction here. You see that there are some corners in this obstacle. And this is kind of like the effect that you see when you're trying to recover a corner, when you are recovering, try to recover a corner with a trigonometric series. It's Gibbs phenomena that is represented here in this. So we realized that the best idea would be to apply a filter to kind of try to decrease the Gibbs phenomena in our reconstruction. And this is applying this filter with different, it's a Gaussian filter that is applying the coefficients. And this is what we get with different sizes of the filter. And this filter, like on the right, you are filtering a little bit more than on the left. And I'm sorry, I think I passed a little bit of the time, but the conclusions are we are able to accelerate the solution of the forward problem using this forward solver using the axis-symmetry with the separation of variables and Fourier decomposition. And we present this two-part framework that is able to reconstruct both the axis of symmetry and center of the obstacle, and also the shape. And one of the advantages is that if we apply that filtering, it's possible to obtain the sharp features of the obstacle when you're doing the reconstruction. Yeah, thank you. Sorry.
Thank you, Carlos. Thank you very much.
You're welcome.
We have some minutes for questions or comments.
So I have just one question. So that's the part that I work on. So at some point you were saying when you have to reconstruct, you were like, yes, TSVD, Tikhonov, you know, any of these methods. But how sensitive is your solution to that method?
So what happened is that this was developed to do everything without noise. The sensitivity is going to depend on the noise that you have there, right? Always. And that is going to be pretty much the limit of where you recover. But we were actually, the idea when we were playing with this method is that what if we don't have any noise and we can recover this up, you know, up to infinite frequency and do like it's the asymptotic behavior of the method. So if you don't have any noise and everything and you apply this method, you can recover everything up to machine precision. But with the noise, the limitation is going to be there, and we avoid Tikhonov because we believe that in Tikhonov we lose a little bit of control of what we are doing when we are doing this entire. Pretty much when you are trying to do Tikhonov, it is very similar with what we did there, right? The Tikhonov is going to set a limit below, and pretty much all the frequencies below that Tikhonov you are throwing out. And that is pretty much what we are doing, and throwing out everything. So all of them are kind of similar to a sense.
Thank you.
We have one more minute if there's any other question or. Well, thank you very much, Carlos, for the interesting talk.
You.
I don't know if we can like clap here. There's a way to do that. Okay.
Yeah, thank you.
I have just found it. Well, thank you very much. And we are in time for our next speaker. Marcela, you can present. You have tried already to.
Ahí voy.
Okay. Our next talk, the title is A New Toric Radon Transform and its Application in Imaging. Marcela Morvidone from the Universidad de San Martín will give the talk. Thank you, Marcela.
Bueno, yo voy a hacer la presentación en español, mis transparencias están en inglés. Lo que voy a presentar es un trabajo de Javier Seveiro durante su postdoctorado en el Centro de Matemática Aplicada de la Universidad de San Martín. También colaboraron Diana Rubio, y también del Centro de Matemática, y dos investigadoras de Francia de la Universidad de Cergy-Pontoise. Este trabajo fue publicado hace poquito, en abril, en un número especial dedicado a desafíos modernos en imágenes de la revista Inverse Problems. Primero, lo que voy a presentar es la motivación de este trabajo. Se trata de una nueva propuesta de métodos de imágenes en 3 dimensiones, del tipo imágenes tomográficas. Voy a luego mostrar el planteo matemático por medio del modelo matemático que describe cómo se toman los datos en este sistema de imágenes. Luego vamos a mostrar que la transformada que describe esa toma de datos es inversible, con lo cual estoy asegurando que puedo recuperar el objeto que estoy estudiando, y finalmente mostraré unas simulaciones numéricas. Entonces empezamos con la motivación de este problema. El sistema de imágenes que proponemos se basa en el efecto Compton, en la dispersión Compton. Lo que sucede con la dispersión Compton es que, bueno, los fotones viajan en trayectorias rectas, pero pueden interactuar, al encontrarse en su camino con electrones, pueden cambiar, desviarse de su trayectoria, y se dispersan a un ángulo que aquí llamamos omega, y que está relacionado con la energía que le queda al fotón después de esa dispersión. Porque el fotón viene con una determinada energía, al interactuar con el electrón pierde un poco de esa energía, se la pasa al electrón, y bueno, la energía del fotón dispersado es menor que la energía del fotón incidente, y esa energía está relacionada con el ángulo de dispersión. Y es gracias a esa relación que podemos tener idea de, al medir supongamos que tenemos un detector que logra medir a una determinada energía, entonces a esa energía sabemos cuál es la dirección desde la cual pueden provenir los fotones que estamos midiendo. Esta es la fórmula de Compton, la que describe la relación entre el ángulo de dispersión y esa energía. Entonces en esta fórmula tenemos la desviación que sufrió el fotón, la energía que le quedó después de la dispersión, la energía del fotón incidente y, bueno, la energía del electrón en reposo. Entonces, el sistema de imágenes que se propone consta de una fuente de radiación que es puntual, vamos a llamarla S, y que localizamos en el origen de coordenadas. Y de un detector que también es puntual. Este detector tiene que ser sensible a los distintos niveles de energía. Justamente porque lo que queremos medir se basa en la dispersión Compton. Y el detector se mueve a una distancia constante de la fuente de radiación. Entonces se mueve sobre una esfera. Vamos a describir la posición del detector usando alfa y beta, los ángulos en coordenadas esféricas, y R es esa distancia constante a la fuente. Como vamos a ubicar el objeto que queremos estudiar fuera de la esfera de detección, es decir, más allá del detector, lo que vamos a medir es la radiación que se dispersa hacia atrás. decir, cuando viene el fotón y choca con el electrón, puede seguir hacia adelante o ir hacia atrás. Bueno, lo que estamos midiendo aquí es la radiación retrodispersada. Por lo tanto, el ángulo de dispersión está entre pi sobre 2 y pi. Entonces les voy a mostrar una animación que ilustra esto que les estoy contando. Tenemos aquí la esfera de detección, donde se encuentra el detector puntual, en este caso, en esta ubicación, dada por el punto verde. La fuente de radiación está en el centro de la esfera. Y el objeto, bueno, está representado por este elipsoide. Entonces, cuando salen los fotones desde la fuente, interactúan con los electrones del objeto y en esos puntos rojos. Y bueno, como tenemos el detector puesto como para que mida una determinada energía asociada a un ángulo de dispersión, todos los lugares de interacción están ubicados sobre un círculo. Y entonces, cuando yo mida en ese punto de detección, todos los lugares donde pudo haber interacción y que yo estoy recibiendo en ese detector, están sobre esta superficie esférica, que es un toro de tipo manzana, se llama, por la forma esa que tiene. Bien. Entonces, vuelvo a mi presentación. Tenemos ahí otras dos representaciones de los toros. Cuanto mayor es el ángulo de dispersión, más grandes son los toros. Entonces, el modelo matemático que representa este sistema de imágenes está dado por una transformada de Radon tórica. Para ello tenemos, digamos, para plantear el modelo, tenemos que parametrizar las superficies tóricas. La parametrización consta, bueno, depende en la parametrización de los parámetros gamma y psi, que son las coordenadas esféricas, los ángulos, digamos. La parametrización del toro tiene una parte angular, una parte radial, donde está la información del ángulo de dispersión, y una parte angular, donde se encuentra la información de la posición del detector. Entonces, cada toro tiene fijos los parámetros omega, alfa y beta. Es decir, un triplete de esos valores fijos me determina un toro, me describe un toro. Bueno, y vamos a llamar ese sub-H al lugar donde vive el objeto, que es una esfera hueca. En el hueco de la esfera está la esfera de detección, y el objeto vive en esa esfera hueca. Entonces, la ecuación que describe el registro de los datos está dada por una integral de superficie. Integro sobre cada toro la f, que me está representando el objeto que quiero estudiar. Esta f es la densidad electrónica del objeto en realidad, porque estamos hablando de este fenómeno de Compton. Los electrones entran en juego. Entonces, explícitamente, la fórmula viene dada bueno, por esa ecuación, y esta transformada de Radon entonces nos modela los datos que recibe el detector. Para demostrar que para unos datos dados existe un único objeto que pudo generarlos, es decir, que para una transformada de Radon dada existe una única f que generó esa transformada, vamos a pasar al dominio de las frecuencias. Aquí en 3 dimensiones, esa representación la vamos se basa en los armónicos esféricos, la descomposición en armónicos esféricos. Los armónicos esféricos son estas funciones en las cuales intervienen los polinomios asociados de Legendre. Cuando el orden de estos polinomios es 0, tengo los polinomios propiamente dichos de Legendre, que sí son polinomios, y no los polinomios asociados, que bueno, son un poco funciones que involucran raíces cuadradas de polinomios, potencias de raíces cuadradas. Bueno, entonces, este sistema me sirve para expandir en el dominio de las frecuencias tanto el objeto que lleva en los coeficientes de Fourier la información de la distancia al origen, la información angular viene aquí, en gamma y psi, y la representación en Fourier de los datos. Entonces lo que queremos ver es que hay unicidad entre estos coeficientes. Dados los coeficientes de Fourier de R sub t de la transformada de Radon, existen los únicos coeficientes de f de un objeto que le corresponden. Entonces, la relación que hay entre esos coeficientes viene dada por esta ecuación integral. Es decir, este viene a ser el planteo en frecuencia de la transformada de Radon. Y vemos que en esta relación intervienen únicamente los polinomios de Legendre, propiamente dichos. Estos sí son polinomios. Lo que vamos a ver para demostrar la relación unívoca es que esta integral es, de hecho, una ecuación integral de tipo Abel generalizada con núcleos con un núcleo que tiene ceros en la diagonal. Y hay un resultado que habla de la unicidad de las soluciones de ese tipo de ecuaciones integrales. De hecho, ese resultado fue demostrado recientemente, en el 2017, por Schiffeneder y Almeyer. Y entonces, para ver que, dados los datos G, o dada la función G, existe una única función F que verifica esta igualdad, el núcleo debe satisfacer ciertas condiciones, las hipótesis son entonces esta 1, 2 y 3, debe cumplir condiciones de suavidad sobre este triángulo AB, que es un triángulo que se encuentra en el primer cuadrante, viene a ser como una rampa, la hipotenusa está sobre la bisectriz del primer cuadrante, un triángulo rectángulo. Sobre la diagonal, el núcleo tiene ceros que son finitos, un conjunto de ceros finitos, y son raíces simples, y además existe una relación particular entre las componentes del gradiente del núcleo sobre la diagonal. Entonces, estas tres hipótesis son las que tiene que satisfacer el núcleo en nuestra integral. Primero, lo que tenemos que hacer es llevar esta ecuación integral a la ecuación de tipo Abel generalizada. Para eso, bueno, se hace un trabajo de cambios de variables, utilizamos propiedades geométricas e identidades trigonométricas para llegar a esta relación. Entonces aquí hemos cambiado la variable omega por la variable p. P es el diámetro de los círculos que generan el toro por rotación alrededor del segmento SD. Entonces, ¿quién es este núcleo K sub L? El núcleo está dado por esta expresión que se puede llevar a una forma más simple introduciendo otra notación suplementaria, introduciendo estas funciones desde la Q1 a la Q4. Vemos que estas funciones son todas suaves en el primer cuadrante, no tienen ningún problema. En el primer cuadrante del plano PR, ningún inconveniente. Entonces, tenemos suavidad. Bueno, todas las funciones que intervienen aquí son suaves en el interior del triángulo que nos interesa. El problema para la suavidad puede venir, viene acá, ¿cierto? En la raíz cuadrada de P menos R. Cuando P es igual a R, al derivar, empezamos a encontrar los inconvenientes. Entonces, para ver que la propiedad de la suavidad también la tiene este núcleo sobre la diagonal, lo que hacemos es más trabajo de álgebra y lo llevamos a una forma en la cual es evidente. Esta forma nos muestra que las potencias impares de la raíz de P menos R se anulan siempre, porque están acompañadas de estos factores que se anulan cuando la raíz de P menos R está elevada a una potencia impar. Entonces eso hace desaparecer el problema de la derivabilidad sobre la diagonal. Entonces el núcleo es suave en la diagonal. Para mostrar las otras dos hipótesis, se siguen haciendo otros varios cálculos algebraicos y se llega a otra expresión del núcleo. Entonces, aquí lo que podemos ver es que cuando P es igual a R, la línea, digamos, el segundo término y los términos que están abajo, en el renglón de abajo, se anulan todos. Lo único que nos queda es este primer término. Entonces ahí lo que podemos ver, bueno, P acá es el polinomio de Legendre de grado L. Lo que podemos ver es que los ceros de Q, de K, perdón, del núcleo, van a ser como, o van a estar relacionados con los ceros del polinomio de Legendre. Y esa Q4 es R mayúscula sobre R minúscula, sobre la diagonal. Entonces es fácil ver esa relación directa entre los ceros del núcleo con los ceros del polinomio de Legendre. Y bueno, como los polinomios de Legendre tienen ceros finitos y son raíces simples, bueno, lo mismo sucede con los ceros del núcleo. Y bueno, para demostrar la última, que se cumple la última hipótesis, también se recurre a esta fórmula, porque esta permite evaluar fácilmente las componentes del gradiente de K en la diagonal. Toda la línea de abajo desaparece porque las potencias de P menos R son todas mayores o iguales que 2. Entonces, al derivar y evaluar en P igual a R, desaparecen esos. Y la expresión que nos queda es fácil de evaluar. Y se ve que se cumple la tercera condición para poder aplicar el teorema de Schieffeleder y Allmayer, que nos dice que dados los coeficientes de Fourier de la transformada de Radon, existe una sola función que pudo generar esos coeficientes. Entonces tenemos ahí demostrada la invertibilidad de la transformada de Radon. Esto lo que hace es asegurarnos que el método que estamos proponiendo vale la pena, es decir, que lo que logremos medir con el detector está representando de forma unívoca el objeto que queremos estudiar. Hemos hecho algunas simulaciones numéricas discretizando la relación entre la transformada de Radon en el dominio de Fourier, y resolvimos el problema numéricamente, el problema inverso, usando regularización de Tikhonov. Si este es el fantoma, estas son secciones planas del objeto que queremos estudiar, Vamos este sería el objeto original. Vemos que tiene algunas quebraduras, digamos, esos detalles pequeños que son detalles de interés y que uno quiere recuperar. Entonces, los datos que va a recibir el detector tienen esta pinta. Esto es lo que sería el sinograma en la tomografía computada. Y después de usar Tikhonov y la transformada inversa de Fourier, recuperamos el objeto. Esto es, en el caso en el que no hay ruido de por medio, vemos que se recupera la información que podríamos pensar que son defectos, quebraduras. Aún si hay un poquito de ruido, se siguen viendo, y con más ruido, bueno, aún así se puede distinguir en la falla. Bueno, entonces eso, aquí termina mi presentación. Agradecemos a los sponsors y un poquito de la bibliografía expongo en esta transparencia. Muchas gracias.
Bueno, muchas gracias, Marcela. Tenemos un ratito, porque tenemos unos minutos más para preguntas. Thank you very much, Marcela. We have some minutes for questions or comments, because our next talk is at 5.
No se entendió nada.
Well, we thank you again, Marcela, if there's no questions. We thank you again, Marcela, and wait for
Bueno, gracias a usted.
the next speaker, couple of minutes. María Gabriela, ya probaste, ¿no es así? ¿Ya probaste compartir? Ok, ok.
No te escuchamos el audio, al menos yo no lo escucho. We can't hear you.
¿No?
¿Me escuchan?
Sí. No, te preguntaba si ya habías probado la charla.
Sí, sí.
Ok.
We can talk.
We
But
can
yes.
also introduce ourselves.
Yeah, we can start with that, because what we would like at some point at the end of each day is to have kind of a networking where first, if people still have questions about the talks and want to ask more questions, they can, and then also, just to introduce ourselves, to say, a little bit more who we are, and this also includes the audience, right? So not just the speakers. So if someone wants to say, yes, I work on this, and wants to chat more, yeah. Yes, I'm Malena. Maybe I can start. Well, we are waiting. So I'm Malena Espanol, and I am at the Arizona State University in the States now, but I did my undergrad at the University of Buenos Aires, UBA. And then I moved to the States. But I work in inverse problems. My expertise is more in numerical linear algebra, developing algorithms like Tikhonov and that part. Yeah. So who wants to go next?
I can continue. I am María Parecki from the University of Buenos Aires, and I stay in Buenos Aires for my life. I have been working in inverse problems, and now especially those inverse problems where there are fractional operators, fractional derivatives, and now I began working on that. Next.
Mariela, the
yes.
other
Okay.
organizer.
I'm Mariela, and now I'm doing my PhD at the University San Martín. I'm not working now with inverse problems. I'm working with machine learning problems and satellite images. I'm trying to make maps of vegetation of wetlands. So I don't have to be in this session.
But Mariela, depending how you look at the machine learning,
Yes, I know.
they are all inverse problems, right? So
Yes, they are inverse problems, but I'm not in the theory of inverse problems. So I don't know if someone wants to continue. We have 4 minutes. Gabriela?
Okay, I am next. I am Gabriela Messineo. I am from Mar del Plata. I am engineer. I am not mathematician. So I am terrible in English. Sorry. My work is mostly applied, not theoretical. So as you will see in my talk, I work with material characterization, and I am exploring also something of machine learning, especially neural networks now.
Okay.
So.
Silvia, Shigola, do you want to go next?
Por tener las cámaras encendidas.
Okay.
Yes, that's the reason.
Okay, I'm Silvia Gigola from the University of Buenos Aires. I made my degree in mathematics in the University of Universidad del Sur in Bahía Blanca. Now I'm working in inverse problems, especially in matrix inverse eigenvalue problem. I made my undergrad my degree in this kind of problems. Now I'm working also in this in inverse eigenvalue problem, especially in 2 kinds of matrices that I'm going to explain in my talk.
Well, we have time for one more because we have 2 minutes before 5. Nobody wants to introduce? That's it? Except now? Okay.
we'll continue with introductions later.
Yes. Gabriela, do you want to ¿querés compartir la pantalla? We are
Yes.
Just in time.
Okay. Should I begin?
Yes, compartir la pantalla.
Yes.
Our next talk, it's mechanical characterization of trabecular bone, and María Gabriela Messineo will give the talk.
Thank you. Thank you. Well, I'm part of Material Mechanics Division in INTEMA, the National Institute of Research in Material Science and Technology.
Discúlpame, Gabriela, yo
yes.
lo veo un poco chico, no sé si todo el mundo lo ve así en la pantalla. ¿Cómo lo ven? Yo lo veo un poco chico.
Bien.
Yo lo veo bien.
Ok, seré yo entonces. Ok.
Okay. No, it's okay. Our main interest in our group is modeling and characterizations of material components and structures. And in particular, we've been working in bone characterization with 2 aspects in mind. The development of biomimetic structures or scaffolds to serve as support for bone regeneration, and the assessment of fracture risk caused by the bone deterioration, which is a consequence of bone diseases such as osteoporosis. This last one is the issue of this talk. During last decades, life expectancy has increased worldwide, and with that, bone diseases such as osteoporosis have proliferated. Osteoporosis leads to the loss of bone mass and increases the fracture risk. This causes an enormous cost to the social security system around the world, so a better understanding of bone mechanics is necessary in order to improve the diagnosis and treatment. Well, bone is a hierarchical structure which can be studied from the macro scale, where the complete bone can be observed, to the nanoscale, where we can see even the collagen microfibrils. Our study focuses on the microscale, where cortical and trabecular bone can be distinguished. Cortical bone is present at the outer face, generally, is present at the outer face of long bones, such as femur, for example. It has low porosity, and it has primarily biomechanical support and protection function. On the other hand, trabecular or cancellous bone is a highly porous material, where trabecula are observable, and it has homeostasis and support function. Homeostasis is the mechanism that equilibrates the cyclic destruction and regeneration of bone. And in osteoporotic patients, the formation of new bone does not compensate the resorption, thus weakening the bone and increasing the risk of fracture. So the characterization of trabecular bone is relevant to understand its behavior. Quantitative ultrasound methodologies are suitable for in vivo bone evaluation, as transmitted ultrasonic waves brings information about the mechanical properties of bone. This technique measures the speed of sound and the broadband ultrasonic attenuation. In an in vitro transmission test, the speed of sound can be measured placing a bone sample in a water tank between a wave transmitter and a wave receiver. Experimental studies have demonstrated that speed of sound is highly correlated with the bone volume to total volume fraction, that is the mineralized bone per unit volume of a sample. This suggests that bone volume to total volume also may be a good candidate for fracture risk prediction. So the main objective of this work is to develop a procedure to compute the bone volume fraction from speed of sound data by means of inverse analysis. The procedure is based on an analytical model posed in terms of geometrical and elastic parameters of bone, which in turn result to be related to the volumetric fraction. So the speed of sound can be put as a function of bone volume to total volume only, and the estimation of the bone volume to total volume is found by minimizing the difference between the speed of sound measured in a transmission test and that calculated with the analytical model. As we know, an inverse problem requires the iterative solution of the direct problem, and in classic models, such as finite element or finite difference, the problem of our concern, where an ultrasonic wave propagates through a material, implies not only fine spatial discretization, but also fine temporal discretization. Besides, as some of the parameters are geometrical, its variation during the optimization results in a whole new structural configuration, and with that, a new machine process. As a consequence, it has an enormous computational cost, and therefore an analytical model is appropriate to represent more efficiently the problem. Besides, with the idea of finding the relation between the waveform applied to the sample to the waveform recorded in the other extreme, that is a transfer function, an approach in the Laplace domain can be used. This task has been achieved by Guillem by finding a closed form solution to the equations stated by Biot in his theory for wave propagation in porous solids. The biot theory was developed for porous rocks saturated with fluid, but it has been widely used when attempting of modeling ultrasonic wave propagation in bone, which is a porous material filled with fluid, with the bone marrow. Sorry. The wave equations shown here are based on the original Biot's work and on more recent developments in poroelasticity for anisotropic materials such as bone. Here we display the wave equations, which are in terms of the displacement vector of fluid, solid and fluid related to solid, the strain and the interstitial pore pressure. And the material parameters here are the solid density, the fluid density, the mixture density, the porosity, and the second order symmetric tensors related to solid phase permeability and sample tortuosity. And these are the constitutive equations for poroelastic materials. They relate the strain, the stress, and the pore pressure, and the related displacement involving the drain elasticity tensor, the Biot effective stress tensor, and the Biot scalar modulus. Let's see now the solution to these equations, which is found by using Laplace transform. Let's assume a porous solid domain, which is the bone domain, laterally unbounded, surrounded by fluid. Here we can separate the fluid in two domains, one between the wave source and the sample, and the fluid beyond the sample, where the receiver is placed. Human bone can be considered as an orthotropic poroelastic material. Then the study can be achieved in its principal directions, where only compressional waves are present. There are no shear waves in this problem. Then the wave propagation can be described as a one-dimensional. So we have one-dimensional governing equations in the fluid and the one-dimensional version of the equations in the porous solid. Here, a dot means differentiation with respect to time, and prime means differentiation with respect to space. The conditions at the interfaces, fluid solid, and the boundaries involve continuity of velocity, pressure, and stress fields. Here we have similar equations for both interfaces, where P sub 1 and P sub 2 are the pressure fields in the fluid at each side of the sample. The excitation wave emitted by the source is P sub 0, which is equal to P sub 1 when it arrives to X sub S. And P sub 2 tends to 0 as X tends to infinity. That means that there are no reflected wave back to the sample. Well, as I said before, the solution to this equation is found in the Laplace domain by using the Laplace transform with respect to time. Then the transform functions are in X and S, where S is the complex Laplace variable. We are looking for the solution of the pressure waves. So transforming the wave equations, the solution for the pressure waves in the fluid can be obtained, are those expressions below, where the boundary conditions have been used. P sub 1, the capital P sub 1 and capital P sub 2 are constants to be determined in base with the boundary conditions with the solid. These are the wave solutions for the porous solid in the transform domain, stated in terms of the pressure and the displacement in the solid. And the general solutions to these equations also can be written in the Laplace domain. Putting the solutions in the wave equations, we can write that equations in matrix form, and the four roots of the system can be obtained. Then the solutions result in terms of lambda sub I, which are the roots of the system, the eigenvalues, the system of coupled equations. And U sub I and P sub I are also constant. Using the continuity conditions at the interfaces, the constants P sub 1 and P sub 2 can be found. And because of the complex expressions obtained for the functions in the Laplace domain, the inverse transform is achieved numerically using a quadrature convolution method. So this is the analytical model that we have used to represent the ultrasonic wave transmission through bone to compare the waves obtained with those from the experiments. We see here the simulated wave at the receiver location in one of the samples. Let's observe that a slow wave and a fast wave can be distinguished just as the Biot theory predicts. In order to determine the speed of sound, we are only interested in the fast wave, but this waveform carries more information that can be used for a deeper understanding of bone. About the experiments. In this work, we've used simulated in vitro experiments. A trabecular bone is an orthotropic material, and so we simulated the test in the three principal directions. The simulations were done with the finite software time derivative, with the finite difference time derivative software Simpsonic, which is a free software for ultrasound propagation. And the geometries were obtained from the microtomography images of 23 samples of trabecular bone, of bovine trabecular bone. And from these simulations, the speed of sound, it would be the experimental speed of sound was obtained using the transmitted wave amplitude versus time data that shown in figures at right. This is the setting of the simulated experiments where a tomography image is shown. From these tomography images, the identifications of the various characteristics of each sample was achieved. To measure bone volume to total volume fraction, trabecular thickness, and trabecular space, the samples were processed with bone shape, which is a specialized free software to analyze bone images. The effective elastic and permeability tensors in the principal anisotropy directions were computed using microfinite element models in combination with asymptotic homogenization. And the tortuosity was obtained implementing in MATLAB the Dijkstra shortest path algorithm. The resulting data was used to correlate tortuosity, permeability, and elastic tensor components with bone volume to total volume fraction. All these parameters values were used for the simulation with finite difference as well as for the analytical model stated before. The region of interest for the numerical simulation were cuboids of side length from 7.1 to 18.7 times the intertrabecular space, and the sample were oriented in its principal direction. In the table below, we show the characteristics of solid phase and fluid phase of the bone. The effective elastic tensor as well as the permeability tensor have been computed using asymptotic homogenization scheme. This method considers three scales: the microscale, where the bone size, which is the bone size scale, and is where all the properties are valid; the sample scale with characteristic length L; and the microscale, which in our case is the scale where the trabeculae are distinguishable. It is assumed that a representative sample can be considered where the characteristics are also valid, that is the representative volume element. Let's focus now on the elastic tensor. The macroscopic strain and deformation are the volumetric averages of the respective microscopic fields. And these fields are related to each other through the microscopic elastic tensor. As the problem of our concern, this problem, is linear, the microscopic strain can be considered as a linear combination of unit deformation states shown here. Here we have 3 axial deformation and 3 shear deformation. Here the superindex denotes the unit deformation and the subindex indicates the components of such deformation. Once the microscopic strain is calculated for each unit deformation, a fourth order tensor M, called localization tensor, can be found. This localization tensor relates to the microscopic strain, and then going back to the stress equations, we found that the relation between the stress and the strain is stated through the fourth-order homogenized tensor C. That's what we are looking for. In general, the elastic tensor is the elasticity tensor is defined by 81 different coefficients. Also, due to symmetry and elastic energy requirements, they reduce to 21 different elements. And for simplicity, we use here Voigt notation that allow us to represent a fourth-order tensor as a matrix of 6 by 6. So we have only 36 coefficients. And we are interested only in C11, C22, and C33. So here we have the results for the effective elastic tensor for the 23 samples as a function of the volumetric fraction of bone. And we can see that there is a clear relation between the constant and the volumetric fraction of bone. And we use these simulations with the analytical model. Well, the permeabilities in the three principal anisotropy directions were also calculated using homogenization schemes, but in this case we use Navier-Stokes microfinite element analysis for incompressible fluids. The calculus is analogous to the one for the elastic tensor, only that here we use 3 loading cases instead of 6. In order to induce one-dimensional flow, the boundary conditions consist in the specification of a pressure gradient and specific slip conditions. Then, using Darcy's model, permeabilities were calculated according to the velocities computed with the finite element analysis. So we have the permeability in the 3 principal directions, and here's the graphics, with the ordinate axis in logarithm scale. Despite the dispersion of the result, the exponential fitting works pretty well, and besides, preliminary studies show that the permeability has negligible effect on the wave velocities. And finally, we calculated the tortuosity in the 3 principal directions. The tortuosity of a bone is a geometric parameter that gives an idea of how intricate the pores are. Low tortuosity means that the pores are almost straight. A high tortuosity value means that the pores have many curves. This value was calculated with the shortest path algorithm formulated by Dijkstra and implemented with my lab. And geometric tortuosity is defined as the average of the true path through the sample over the sample length. Here we have the graphics of the results in the 3 principal directions. Clearly, tortuosity increases with the bone volume fraction, and although it has some dispersion, it is less important than the one for permeability. So, the computed parameters were used to simulate the ultrasonic wave propagation through the material with the finite difference software as well as with the analytical model. With the finite difference software, we used the actual values, the measured values. And in the analytical model, the parameters were put in terms of the fraction volume according to the fitting shown before. In the case of the elasticity and the tortuosity, we found a linear approximation, whereas in the case of permeability, the relation is exponential. In these figures, we can see the waves simulated with each model in one of the 23 samples. And the difference between the waveforms can be attributed in part to the fact that in the finite difference simulation, which is on the left, the only mechanism of attenuation is the scattering, whereas the analytical model also accounts for a dispersive viscous attenuation. That is an attenuation that depends on frequency. Also, the waveforms are quite different. It is clear that the velocities in the principal directions are in good agreement. And here, the relation between the velocities simulated with both models is shown. We can see that in most of the samples, this relation is near to 1. It is bigger than 0.9 in most of the cases. And this encourages us to use the analytical model in the inverse problem to estimate the bond volume to total volume from the minimization of the difference between the velocities. So the cost function of the inverse problem is the mean square error of the velocities with all the analytical parameters as a function of the volumetric fraction of bone. And the minimization was implemented with MATLAB function fminmax, giving an optimal value of bone volume to total volume for each sample. In this figure, the optimized values of the volume fraction versus the measured values in the samples is shown, along with the theoretical line. We see that there is a good estimate in most of the cases, being the error around 18%, and with standard deviation of 25%. So we can conclude that the proposed procedure allows for acceptable estimation of the solid fraction of bone, which could be a good fractal risk prediction tool. We intend to keep on working further, addressing the effects of attenuation into the model in order to extend the analysis to incorporate broadband ultrasonic attenuation. We are going to thoroughly study the sensitivity of all the parameters. Although some study has already been made, it is not yet well documented. Also, we are going to investigate the influence of the error in the approximation of the measured parameters on the error in the estimation of the solid fraction. And finally, we plan to develop new procedures to explore the possibility of extracting more information from the waves. This has been a joint work with Professor Adrián Sicilino and Joaquín García Zárate, which was a PhD student. And I'd like to thank to Professor Gloria Frontini for her guidance and support through many years of working together. And thank you for your attention.
Well, thank you very much, Gabriela.
You're welcome.
We are very good time. So if there's any question or comments.
Hi, can I make you questions?
Yes, of course.
Hi, nice to meet you. I'm going to, can it be in Spanish? I think it's more simple for the questions, or what you want. No, tengo una duda un poco. Cuando tú hablas de huesos, hay en mecánica sólidos, ¿verdad? Uno habla de materiales que le llaman materiales quebradizos, los brittle materials que le llaman.
Sí.
Sí. ¿Los huesos están considerados dentro de esa clase?
Ahí se cortó.
¿Y por qué voy un poquito con eso? Porque este tipo de cosas yo creo que son súper interesantes cuando estás estudiando mecánica de roca. También la roca es considerado un material quebradizo y hay muchas aplicaciones y problemas asociados al fracturamiento hidráulico que aparecen en el petróleo, en los gases, cuando sacan gas, ¿verdad? Minería subterránea y ahí un poco que me parece súper interesante lo que mostraste, sobre todo también para hacer validación cuando uno va a casos reales. Entonces era un poco esa mi pregunta, o sea, más que nada una cosa muy general. Eso.
Se cortó un poquito, no llegué a entender del todo la pregunta. Era si los huesos pueden ser considerados...
Sí, pueden ser considerados materiales de estos quebradizos, los brittle materials que le llaman, porque como te decía, ese tipo de materiales, hay una gran clase de materiales como los cerámicos, como las rocas y eso, que están considerados entre esa clase y parte de esto uno podría pensar que puede ser aplicado a problemas de interacción fluido-estructura como el fracturamiento
Sí.
hidráulico, cosas de esas.
De hecho, la teoría de Biot está desarrollada para rocas. O sea que sí, es muy similar la mecánica, me imagino yo. I don't know if I say it in English. I said that the Biot theory was developed for porous rocks. So, and the people who works with bones took that theory and tried it on bones, but it was especially developed for rocks. So yes, it is quite similar. This spongy bone, especially.
Okay. No, thanks a lot, because as I told you, the hydraulic fracturing, which is very well applied in inverse problems for oil extraction, gas extraction, underground mining, and so on, there are a lot of open questions there, and maybe this kind of works can help to understand the mechanics, which what happened there when you have a very big stress around 30 megapascal and so on. Then I think it's very interesting, and
yes,
I think it's very interesting for me.
Thank you.
I think there's another question. There's somebody that have raised a hand. Elsie Orlando, you can ask.
Hi, Elcio.
Yes,
Hi.
me. Hello, Gabriela. Good to see you.
Lo mismo para vos.
¿Está bem?
Muchos años.
Tudo
Yes.
bem?
Todo bien. Extrañando la gloria.
Abraço à Glória e a Guilherme também.
Le digo.
E todo o personal do laboratório.
Sorry?
E abraço a todo o personal
Muchas gracias.
do laboratório.
Gracias.
Well,
Yes.
good afternoon. Thank you, Maria Inês, Mariela, Malena, for inviting me to be in this session. It's a pleasure to be here. And Mariela, or Gabriela, I'm sorry. My question is, you have examined different models, right? And they, at the end, when you estimated the parameters,
Yes.
there are some experimental data that cannot be actually fit by the model.
Yes. Can I share my screen again?
And my question is, if you think that this is a problem with the measurements or it's a problem with the model. We can see that there are some around 0.2, there are some measurements that are really off the model, right?
You said this?
Yeah.
Yes, these were terrible. We can erase that.
Okay, so it's a problem with the measurements, actually.
I don't know. I don't know if it is the measurements. Actually, the images tomographies are quite different from each other. I show just one here, but maybe I don't know, because it has the same bone volume. If you look here, you have two samples with the exact bone volume, total volume fraction, and the estimate is completely different. So that is one of the things that we need to keep working on. We need to study how the errors in the estimations of the parameters ¿cómo se dice influye?
Yeah, influence.
Influence, okay. The estimation of the total volume, of the volume fraction, sorry. I don't know if I answer your question.
Yeah, I'm thinking if this could be something related to the model itself, if the model would be appropriate for some cases and not for another case.
Maybe. Yes, maybe it could be. Yes, but we have not studied that yet. This was a work from a PhD student, Joaquin, with us as directors, and he resigned to the scholarship.
Mm-hmm.
So we have to continue working on this ourselves
Okay.
now. Yes.
Okay. Gracias, gracias.
Gracias, Elsa.
Gracias. Prazer te ver, Gabriela. Um abraço.
Igualmente, igualmente, un abrazo.
Sim, gracias, gracias.
Another question. Well, then we thank you again, Gabriela, and
Thank
we'll
you.
return at 10 to 6. Is that right?
All right.
Thank
Thank
you,
you.
everybody. See you.
Thank you.
Thanks.